To start where we left off last time, we were talking about our third application of the right-hand rule. So, first one, remember, is if you are looking at a straight wire, any wire really, but a single wire generally, and you want to find the direction of the magnetic field, you use the right-hand rule. So, point your thumb in the direction the current is going in that part of the wire. Your fingers curl around in the direction of the magnetic field, and it's always going to be a circular around that wire. If the wire changes, you'll have to consider it a little differently. If we have a solenoid, which is a coil of wire like so, and we can identify what direction the current is going, so if I were inserting the current on this side and come out here, the current would be going this way. We'd wrap our fingers around, and our thumb points in the direction of the magnetic field inside the coil. So to reiterate that one, let's draw it up. If we had a coil, and I'm just going to draw it like what you'll see on the homework. And current comes in this way, so it's going up this visible part, and then it'll go like this. We curl our finger around. Magnetic field inside the coil would point to the left. And then this becomes then the North Pole, South Pole. This is exactly what it would look like inside a regular magnet. And then curl around like this, just like a regular bar magnet.
Do you put that in the boxes?
What's that?
Do you put that in the boxes?
Yeah, essentially. I mean, you could put an arrow at that point. Now, as we ran out of time last time, we were talking about a third use of the right-hand rule, and this one dealt with what happens when we have a moving particle or moving charge inside a magnetic field. We showed that it disrupted a television because that is this sort of, the tube television has electrons being shot at the screen, so bringing a magnet close deflects those and changes the color on the screen. Similar sort of thing. So let's say that we have a particle, a charged particle, and let's, for the sake of ease, make that a positive particle. And we'll say that this positive particle is moving to the right. And we'll also say that it's moving to the right in an area, well, let's do it right angles to begin with, in an area with a magnetic field pointing in this direction. And we want to say, what direction is the force? We can also apply the right-hand rule to this. This is the little more complicated, put your right hand so that the thumb and first two fingers are all at right angles to each other, or orthogonal. Sometimes this is really showing the XYZ axis system. And I've got it illustrated up there. We've got three different things that we're looking at for these three fingers. One of them is F, force. One of them is I, current, which is the same direction as a velocity. So these are both technically vectors. And then we've got a third one, magnetic field. To help you remember, so we've got FBI. Sorry, I'm going to put those in a different order. Yeah. To help you remember which finger's which, think about F. Okay, that's going to be the force, and it's the natural finger for such use. Then it will go in order, FBI. Okay? So when we are using this, what we want to do is line up two of these with the knowns. So we know the direction of movement of the charge in this one. That's current. So that would be the I, our thumb. So our thumb has to go in that direction. B is our pointer finger. So that would have to align with the magnetic field, which in this case is up on the board. Force then is your F finger. So the force in this case would be coming out of the board. It'd be coming in this plane. So if this were a moving charge, it would actually be bent out towards us.
What's below current?
Oh, sorry, I didn't do that neatly. Parallel to velocity.
Is this solenoids?
This is moving charges.
That'd be this one.
Okay, so the force here would be out of the board. Oops, green on that. Which is a dot if the arrow's coming at you. Yes, Matt?
So, current would be the direction it's moving?
Current is a direction it's moving. Current is always a positive direction, though, or a positive movement. Let's say that instead of, say, a proton, we had an electron. Yes?
I was just going to ask if B can ever be down, but I'm guessing.
Oh, yeah, absolutely. B could be in any direction. Yeah, we don't know what direction it is. We just have to apply the right-hand rule based on what is happening. Yep.
So wouldn't that mean that the force would always be coming at you? Because if you change the, it'd just be going around.
We will explore that in just right after we talk about this bit, too. That's a good question, though. Let's talk about what happens if you have a negative particle here. So when we were talking about electricity, we said current always goes in the direction of positive particle flow. But technically speaking, electricity is the flow of electrons the opposite way. Everything still works out normally if you reverse this direction. The way I suggest doing it is do it just as though it were positive. So we'd still have the current that way, the field this way, force coming out, but it's negative. So what is negative that way? That way, into the board. So if this were a negative charge, it would be, the force would be into the board. Yep.
How do you know it's supposed to go this way? Because couldn't you always like flip around and then maybe go that way?
Can you?
I don't know.
So you know that they have to be in different planes, right? Right at angles to each other. Can you move if your thumb is that way, in the direction of the motion, and your finger is that way, can you point your finger the other way?
Oh, I thought you could go down. I thought you said B.
Well, you can, but now we'd have current to the right, the field going down.
Well, your left hand
Well,
works.
when can B go down?
Yes, your left hand can, but we call it the right hand rule for a
Or
reason.
you can use the left hand for negative charge.
You can, if you wish. I would suggest not. I would suggest always using your right hand.
Left hand down.
Yeah, yeah.
So this was all assuming, like, when we were doing this, that a positive is the negative way?
I just put that.
And then, yeah, it'd be, so if you're ever dealing with a negative charge, just treat it as though it were a positive, but realize, oh, at the end I have to flip the direction, because it will be a negative in that direction. Yes?
Will it always give us B so we know which way to point?
Not always. I might ask you, B.
Oh,
You know,
so
what
it's-
direction would the magnetic field be in order to get a force in this direction? And then you just, okay, I know the direction of force. You're always going to know too.
So are we going to be on the test? So like this?
Yeah, it's awesome. I might even record the test. Just, you know.
Yeah, that's what the homework said last night.
Yeah, that's good. I love that. Let's talk about Cody's question here, though. What happens at different directions? Oh, you know what? Actually, that's part of your homework. No, it isn't directly. So we'll talk a little bit about that. So let's say that we have our positive particle again, moving to the right. We'll keep that consistent. But now let's put our magnetic field in this direction. We're also going to talk now about how we can find, because you could kind of move your fingers around, but the other thing we left off with was the equation about how to find this force. That the force is equal to QV with a new symbol for some cross B. It's important that that is a cross, it's not a dot, because this is a way to multiply two vectors, the velocity and the magnetic field. So just to recap what we had from last time, F is our force in newtons. Q, just like last chapter, charge in coulombs. V is our velocity, meters per second. And B is our only real new one here, and that is magnetic field strength. In Tesla, which is abbreviated T, capital T. Same where the car company got its name, and after Nikola Tesla. Yeah, it's an electric car. They're really hot. I have sort of an acquaintance in California who bought one. Of course, she also bought a one of the solid golds iWatches, but she likes to throw money around, I think.
When I was in LA, we saw a huge Tesla dealership, and it was like, it looked like a football field. It was so big.
Yeah.
It was awesome.
They're nice cars too. They're really nice. They don't have a huge range, which would bother me. They'd be great for going back and to and from work, but if I had to draw, well, I guess I wouldn't be able to drive down to my in-laws in Omaha, so maybe I should look into getting one.
Wait, what do you mean?
Get
Right?
wrecked.
Their range is like 300 miles on a full charge.
Oh, charge.
Yeah. So great for going to and from work.
You do gas too.
You can't do gas in them.
Really?
The Chevy Volts, you can do gas. And so that's interesting.
That's a hybrid.
Yeah, well, not really,
Yeah.
because it doesn't have a gas engine that drives the car.
But the
It's got a gas generator that charges the battery. So it's a very low power engine in it, but all it does is charge the battery. It's quite efficient for that, and it's a really good choice.
And $60,000.
Is it that much now?
Yeah.
Does it have a specified charging station, or can you use it?
I want to say that you can use 120 volts from your normal outlet, but it would take a long time. So you'd want a 240, I think, dedicated socket for it, and it sucks quite a bit of power, but it is long run more efficient than gas and cheaper.
Over spring break, when we were down in Florida, at like the main parking area, really close to where the place you're going at, they had the charging stations, and there were like a lot of volts parked there that
Yeah.
were charging.
Yep.
Do you think you spend more money on gas or charging a car like that?
Gas, I think. I think it works out quite a bit that way, in the electricity's favor.
A lot again.
It's definitely better pollution-wise,
Yeah.
because electricity is generated much more efficiently than automobiles. Okay, so anyway, now this is a new way. It's called a cross product. It's a new way to measure things. Remember that we did multiply two vectors previously when we were looking at work. F dot B, we called that. Force times the distance, and this is called a dot or scalar product. And we shortened that, or simplified it for our purposes, FD cosine theta, cosine of the angle in between them. But this no longer made a vector. So that's why it's called a scalar product, because work is a scalar quantity, no direction involved. Force, though, is always a vector. And so now we have to have a way to multiply these, but get a vector out. And so this cross product, or vector product, works a little bit differently, but something you'll see. We kind of ignore the vector qualities. Oops, not cosine. And we multiply by the sine of the angle in between the velocity and the magnetic field. So this is where we got into the discussion of what does this mean, where we ended. Means that theta is the angle in between velocity and magnetic field.
So whenever, like for the FD cosine theta, whenever there's just like FD and there's no thing before it, that means it's scalar?
Yeah.
Okay.
Yeah. So you mean no arrows or anything, or
Well,
what?
no, of either the dot or the x. If it's just
You
like
can't. You have to multiply vectors one of these two ways. Since force is always a vector, in order to multiply it by another vector like displacement, you have to choose one of these two ways in order to do it. Since that's how it works out for work, though. Yeah, Matt.
Does charge have a direction?
Nope.
Okay, so you were just saying like its first velocity.
Its velocity is a direction, and so is the magnetic field, though. The charge itself has no direction. It's just it's a unit, or it's not unitless, but it's directionless. It's a scalar. So this is important. Let's talk about then Cody's question, though, and apply it to here, because what we do is we can find the value of the force with this, but we have to use the right-hand rule to find the direction of the force afterwards. So let's find out how much the force is, and then we can talk about the direction. So let's take our positive charge. We don't really care in this purpose for the what value is, and you'll see why. The direction is that way of the velocity. The magnetic field is that way. What is the angle in between those two?
0. Or is it 360?
0. Or 360, I don't care. 2 pi, whatever. What is the sign of 0? 0. What is the force on this particle? 0. So when they're parallel to each other, there is no force whatsoever. It works very differently than other forces we have talked about that are always applying their force in their direction. A magnetic field actually always applies a force perpendicular to itself, and it's got to have a moving charge that is not aligned with it. Any other angle we would have a force that we could calculate, but not parallel. Yeah?
So if your fingers go like connect together, then you don't have.
Then there's no force, yeah. Essentially. It just goes back to this theta is 0, so no force. Okay. Let's see, I think that's what we need to, now we just need to practice.
Yeah.
Just practice.
Okay. So any questions on this stuff, though? Before I introduce you into this fairly simply, the first the worksheet has no calculation on it. It's all what direction is the vector. Yes, Matt.
So this stuff is the bottom half of the 1.8 thing?
Right. Yep. So now we've done everything you need to finish this. What I want to do today is give you work time on this and work time on the next lab, which will be today and tomorrow. So if you get done, then talk about the lab. The lab you'll be working with your group, but you'll notice that the next lab is largely blank. I want you guys to come up with an idea. I can help you implement it with things that I know that I have that you may not. So if you've got questions like, could we use anything like this, I might be able to make a good suggestion. But what you're going to be doing is making a solenoid. I've got thinner wires, so you don't need the thick wires. But essentially, put an iron core in here, like we did in lab the other day, the larger ones. And now we've got an electromagnet. I want you to figure out the relationship of how strong does an electromagnet get depending on the number of coils wrapped around it and the amount of current going through the coils. So it'll be a pair of tests, one testing the number of coils with constant current, one testing the amount of current with a constant number of coils. I don't know if I said that.
Like, should the different thickness of rods change anything?
It could, certainly. That's not really part of this test, so I'd say use one of the beefier ones. I've got them in a bin.